So I will be talking with the topic of computer vision is guiding cranes. And as said in the beginning, so my role in FCAI is now also to introduce the sustainability science into artificial intelligence research. And then therefore I will be now also a bit giving motivation for our research from the sustainability viewpoint. And here it's of course important to remember that of course the climate is one of the most important parts where the sustainability will address and try to develop good systems to cope with that. But also sustainability deals with social and economical topics. So we have the three pillars there. And in our research, we are now, as I said, developing computer vision methods for cranes that operate indoors. And then the motivation for this is that we want to, at some time, have autonomous cranes that could operate indoors and be with very scalable methods, so that we could use the methods for different kinds of cranes for indoors. And then there, for the operations to be safe, we of course need to be able to locate the cranes really accurately indoors. And as you probably know, when we are operating indoors, we can't use the normal localization navigation system. So the satellite navigation doesn't work indoors. And also, if we want to have something that is very scalable, we don't want to equip the environment with some existing or something static infrastructure that we would need all the time when we are localization. So we want to have something that is very scalable. And then therefore we are now using computer vision. But for computer vision, we have quite challenging setup also. So for example, when we are looking at cranes that are operating up on the roof, they usually have the cameras looking down. And as I will show you in the following picture, so there we also have some difficulties for the computer vision arising from the fact that the cameras are looking down at the floor. So this is one of the safety things that we have to then, of course, for the sustainability reasons also to achieve. And then this means, as I said, we have to know the location of the crane, but also we have to understand what is happening around the crane. And therefore also the computer vision is really good method for that. But then of course also we want to get the efficiency benefits for the operations. And then therefore we need to have low cost equipment. So we can't be operating with, for example, the LiDARs are at the moment used quite a lot because they cost easily 10,000 euros. And if we want to have something scalable, we want to have some very low-cost cameras. And also for the sustainability reasons, of course, we need to have low power consumption. And then this means that in this case, we then, when we require these low-cost equipment and the low power consumption, we are then using so-called monocular cameras, so the normal cameras having only one lens. And this is also creating some challenges for the computer vision that I will be talking about a bit. So we have been doing this research in my research group at the University of Helsinki with the donation coming from Connect Cranes. And so we have been quite a lot with exchanging the ideas and trying to also really carefully understand their operation environment there. And then there is also a video of that if you want to look from the FCAI success story setup. But okay, so as said, so now we have the situation, we have a challenging environment, very strict requirements for the systems that we are using, and we are trying to achieve these benefits. And then therefore we are now using the computer vision from monocular cameras and the deep learning that has luckily been many times already described today. So we are using the deep neural networks and to compute how the camera and therefore the crane moves, and also to understand what do we see around the crane. So for understanding the location of something, of the camera from the images only, we usually use methods called visual simultaneous localization and mapping, so SLAM. And it is based on being able to detect how what we can see in the images changes, and based on that compute then the motion of the camera and of the system where the camera is attached. And then also we have to do something called 3D multi-object detection, so to be able to see and understand what is around the autonomous cranes, we have to also detect what there is in the environment. And in the previous, we already saw these examples of the so-called 2D object detection, which is really mature and good method already now. but then in our case we have to turn this into 3D information. And now we are using only the monocular cameras where we have some challenges for this. And I will explain those on the following slide. And then here I'm also now bringing up this quite old-fashioned method that has been used also for, or maybe not old-fashioned, but a method that has been used traditionally for understanding this motion based on the images, something that was done a lot before we introduced this LAM, and you will also see the reason why I'm now using here the term structure from motion, which is something quite similar as this LAM method that probably is familiar for many of you. Okay, but now as I have been mentioning many times that we need to understand the motion of the camera, and also we have to understand the location of the things that we can see in the images. We bump into a problem that arises from using these cheap, low-cost, efficient monocular cameras. And this is that these cameras, they can't detect the depth, so the distance to the things that we see in the images naturally. And this is now creating something called unambiguous scale into our motion computation, so we don't really get the metrics out of there that we would really require. And also the same thing as I said, so we need to turn this 2D object detection information into 3D, so we are not able to do that if we don't know the distance for those different things that we can see in the environment. And there already are good methods based on deep learning to estimate the distance to all the things that we can see in the surrounding. Not perfect yet, but getting quite mature in the research already. But the problem here is that usually these methods, they use different kinds of visual cues that they can see in the environment. So for example, they detect when we use those methods from a vehicle, they can understand that what is the position of the different objects that we can see in the environment with respect, for example, to the road. And then therefore we are able from these probably to estimate what is the depth and the distance to the things that we can see. But here in the image you can see that what is now our problem. So our problem is that our viewpoint is that we are looking down to the floor, which means that we are not able to use these visual cues, and then therefore now also the depth detection is coming quite difficult. And then therefore what we have been doing is that we have taken something of the state-of-the-art camera motion detectors based on deep learning called SFM learners, structure from motion learners, and we have developed those further, developed the algorithms for them to be able to cope with our challenging situations. And then so, as said, so there are really good methods already in the very state-of-the-art literature in computer vision research, and as said, this enhanced structure from motion learner is something that we have been now working with. And the reason why we have taken this structure from motion learner as a basis is that also it has one really good benefit for the research purposes, and also points that we have already been discussing, that when we are now training the networks, we need a lot of data, and if we are doing the supervised learning, we need to label all the data. But in this case, this structure from motion learner, it performs quite well as an unsupervised method. So we don't have to do the labeling. And in this case, we have been then improving the algorithm, so doing there something called angle alignment, and then also multi-image input, and so on, and then improved the whole pipeline so that we are now able to get accurate result also in our very challenging setup and environment. Well, as in research, we always have to then also test our new methods against some benchmark data, and here we have tested some very much simpler scheme than where our images come from, and then we noticed that our method is performing really well, so we are performing as well as the other state-of-the-art methods that have been especially tuned for these a bit simpler cases. So here we have been detecting the depth of things that we can see, that we are then able to turn this into the accurate location and 3D object information. And here you can see on the left is the original image, in the middle is our depth solution, and on the right is ground truth solution, what the situation really is. But as said, of course, then when we are working with these grains and with the difficult indoor industrial environments, then of course we also have to use the realistic data to be able to see how our methods perform. And therefore we've been doing collaboration with Aalto University's industrial laboratory, where they have this Connect Cranes test crane. And so we have been using our equipment, so a simple monocular camera, and then also we have used a LiDAR to get us the ground truth information of what is the distance to the different objects. And by collecting that kind of image set, we have been then testing our own method, and we have noticed that now our method performs better than the state-of-the-art previous versions of this deep neural network-based system. And so we are now able to get improved solution for getting the depth by using these quite difficult industrial crane images. And we have just submitted the paper to a conference, so hopefully we will soon, you will be able then also to read more details about that in the paper. But then also, as I said, so the research continues, so then the next step is, of course, now we are able to get this good solution for the depth information, so then the next step is now to turn and use this information also for this 3D object understanding. So now understanding really where are the different objects that we can see in the environment, for example, the humans and other moving objects that we really don't want to crash when we have the autonomous crane. And then also there are other challenges that you can see here on the images that will also, the research will continue on these. So we have many places where we don't really have any features that the system could be detecting, and also we have these shiny so-called non-Lambertian surfaces that also confuse the computation. And then also the next step, maybe not so much related to the mobile machines, is also then to use these methods for pedestrians, for also getting the good localization solution there. But then also very briefly going back to what Ville already mentioned, so as said, so we have now established a new highlight in FCAI called AI for Sustainability. And the first practical action for this new highlight is then the start of a so-called virtual laboratory together with the research program addressing the autonomous systems. So we have together established a virtual laboratory called Sustainable Mobility and Autonomous Systems, where the goal is now to then develop the algorithms, very sophisticated artificial intelligence methods for addressing many of these big problems that has already been mentioned here today. So for example, closing the reality gap, and then in the future also of using other information now to get also the sustainability benefits, for example, things coming out from CO2 emissions, air quality problems, and even the socio-economical data there. And then so as I said, that the research here continues really strongly also in the future. But okay, thank you. This was all from my side. But